Hello, you crazy cats. We are here. Wait, where am I? Oh, up in that little small square up there. Nope, just kidding. Right here. Hello, you crazy cats, and welcome back to our final video here. It's been a wonderful break. I hope you all had a joyous holiday season. Hopefully you got some cool things, and even more importantly, hopefully you gave some things that like made your heart nice and warm, So remember, giving is always more important than receiving. Take that one to the bank. So let's make this one short and sweet. Try and get through this and let you enjoy the rest of your Christmas break. So oxidation reduction reactions. Oxidation is a loss of electrons. Reduction is a gain of electrons. One cannot occur without the other. They go hand in hand. Okay, we call these oxidation reduction reactions, or for short, if you're reading, it's a redox reaction. Reduction, oxidation, redox reaction. So it's rusting, right? Oxidation is rusting, but there needs to be some reduction that's going on too, because they do go hand in hand. If you take a look at this, we have reactants, calcium metal combining with oxygen. Let me get my little pointer out here. We have calcium metal reacting with the oxygen in the air. This forms calcium oxide. So we have the calcium metal is being oxidized. Electrons are being lost to the oxygen air. Oxygen is reduced. It gains those electrons. And then we have the calcium that has now combined with oxygen to produce calcium oxide. The substance that is oxidized is losing the electrons, while the substance that's being reduced is gaining those electrons. How are you going to remember this? How are you going to remember oxidation is loss, reduction is gain? Well, I got two cool ways to remember it. They are very common in the chemistry world, but I remember them fondly of my high school chemistry teacher, Mr. Ben Savango. Shout out to Mr. Benz if you ever see this or if you're ever watching. I became a teacher mainly for one of the reasons because of you. So Mr. Ben Savango, he taught this to me when I was in chemistry and AP Chem, and now hopefully I could teach it to you. Like I said, it's nothing extraordinary, nothing crazy, but it is a wonderful way to remember it. Two ways: oil rig and Leo the lion says grrr. Oil rig, oxidation is loss. Loss of what? Loss of electrons. Reduction is gain. Oil rig, oxidation is loss, reduction is gain. Easy way to remember it. And another one, Leo the lion says grr. Leo, lose electrons, oxidation. Grr, gain electrons, reduction. Let me hear you say the two. Oil rig and Leo the lion says grr. Did you do the grr? All right, well, hey, those are the two ways you remember it. Excuse me. So oil rig and Leo the lion says grr. All right, so when we're talking about redox reactions, we're talking about oxidation numbers. You know what an oxidation number is, right? It's the charge, periodic table, +1, +2, +3, 3 minus, 2 minus, 1 minus. To determine if an oxidation reduction reaction has occurred, we assign oxidation numbers or charges to each element in a neutral compound. We want to see if those charges have changed during a reaction. Elements in their elemental form have an oxidation number of 0. There's no charge. Calcium metal by itself is a goose egg. It is 0, no charge. But the calcium ion is a +2. The oxidation number of a monatomic ion is the same as its charge. Monatomic ions, you know what these are. We just really haven't talked about a monatomic ion. It's calcium 2+. It's sulfur 2-, chlorine 1-, sodium 1+. It's one thing by itself. You've heard of polyatomic ions. Those are covalently bonded atoms to make up an ion. So monatomic one, polyatomic multiple. I told you we were moving and grooving right through this. Rules assigning oxidation numbers, you know this. Oxygen has an oxidation number of -2, except for the peroxide, which has an oxidation number of -1. Remember your polyatomics. Non-metals tend to have negative, while metals tend to have positive. Hydrogen can be a -1 or a +1, depending on what it's bonded to. The hydrogen ion or the hydride ion, right? Non-metals tend to have negative oxidation numbers. Fluorine is always -1. Other halogens are also -1, but they can also have positive oxidation numbers. most notably in oxyanions. So when they're bonded with an oxygen. So we've seen some of this in our Lewis structures when we look at formal charges. They're starting to pick up some charges. Some of the oxidation numbers for any compound is always neutral. It's always 0. We make sure of that, right? We do the crisscross rules when we have ionics, unless it is an ion itself. The sum of the oxidation numbers in a polyatomic ion is the charge of the ion itself. Oh my God, it's like I took this from somewhere. I did. Full credit. Full credit. Pearson Education. Right down there in the bottom. Copyright 2015. All right, that was redox reactions. So let's take a look at displacement reactions. Displacement reactions is actually displacing something, bouncing it out. So we hear this is a common reaction between magnesium metal and hydrochloric acid. We see that the magnesium metal is getting bombarded with the hydrochloric acid, and that it will replace some of the ions. In a displacement reaction, ions oxidize an element. The ions are then reduced. It's a redox reaction again. In this reaction, silver ions oxidize the copper metal. That means something must have been reduced. That would be the silver. The copper, look at the equation down at the bottom. The copper plus the silver yields the copper ion plus the silver metal. So in this case, one was reduced, one was oxidized. Okay, the silver ions oxidized. The copper was oxidized while the silver was reduced. They have to go hand in hand. So the equation you're looking at is the ionic equation. If you look up at the top, you see the copper metal with silver nitrate reacts to form silver and copper 2 nitrate. Okay, so that's when we're talking about the copper is being oxidized, the silver is being reduced. Okay, the copper is losing electrons, oxidation is loss, while the silver is gaining electrons. Reduction is gain. The reverse reaction, however, does not occur. It doesn't have enough energy. It doesn't want to go back. It wants to fall down. You can't fall uphill. The reason we know this is because we have something called an activity series. Excuse me. Elements higher on the activity series are more reactive. Elements lower are less reactive. The higher those are, the more likely they are to exist as ions. So lithium is more reactive than potassium, is more reactive than barium, is more reactive than calcium, so on and so on. It's more likely to break down and stay broken down. Okay, it doesn't want to go back. All right. So if we were to take a look at the previous example, we see that from this one, copper and silver, copper wants to be oxidized, silver wants to be reduced. Silver does not want to be oxidized, because if we look at this, silver falls below copper right down here. So silver doesn't want to go back in. Okay, silver does not want to release that. Copper wants to become oxidized, but not silver. Copper more so than silver. You see, right? Copper is on top, wants to be oxidized. Silver does not, compared to copper. Metal acid displacement reactions. When we react metal and an acid, the elements above hydrogen will react with acids to produce hydrogen gas. The metal is oxidized into a cation. Yeah. All right, folks. Now we're going to get into molarity and concentration, and we have talked about this slightly. Okay, we remember molarity is a measure of moles of solute per volume of solvent, or excuse me, per volume of solution. We usually classify it as per liter. Moles per liter is a molarity. The quantity of solute in a solution can matter to a chemist. If we want something that's highly concentrated, we have to look at its molarity. If we want something, we need some way to measure concentration, and that's molarity. We call the amount of dissolved its concentration. Molarity is one way to measure the concentration of a solution. There's other ways. There's something called molality, or percent by volume, or percent by mass, but molarity or normality is another one, but molarity is probably the most common. When we mix a solution to create a solution of known molarity, right, because we're talking about moles, we weigh out a known mass. We can therefore convert it into moles using the molar mass. And then we fill usually to an indicated volume, 250 milliliters, 500 milliliters, a liter, whatever. And then we do the calculation. Moles of, however, per the total volume of solution. If we were using, in this case, a volumetric flask, which is the flask that you see down there, and let's say that looks to be about a 250 milliliter volumetric flask, we would take the amount of moles we have that we weighed out and divide it by 0.250 liters, 250 milliliters. That's our solution. From there, we could then dilute. If you have something of known concentration and you dilute it, are you going to make the new solution more or less concentrated by diluting it? Correct, you're going to make it less concentrated. So dilution is a way for us to scale down the molarity. We could use a pipette. You guys know what pipettes are, to deliver the solution to a new volumetric and then again dilute that to an indicated volume. So there are ways to find out what the new molarity would be. So if I, for example, take a 5 molar solution of hydrochloric acid, and I take 5 milliliters of that and put it into 500 milliliters of solution, water, what is my new concentration? What is my new molarity? I went from 5 molar to, I don't know. This equation allows us to do this, all right? It's MV equals MV. MC and VC subscripts C are the molarity of the concentrated and volume of the concentrated solutions, where M sub D and V sub D are the molarity and volume of the diluted solution. So we could use this calculation to find out the new molarity. In most cases, you'll either be calculating the M sub D, the molarity of the new diluted solution, with the 3 other values given, or you will be you have a molarity that you want to reach and you want to find out how much do I pull from the original solution. In that case, you'll be calculating V sub C, the volume that you have to take out of the concentrated solution. So MV equals MV. It's a nice little equality there. You guys know how to do molarities, grams to moles. You're using molar mass, moles to moles, and from there we can go to our concentrations by using our volumes. 2 more slides. A titration is something that we can use to calculate a concentration. We would take an unknown. In this case, the unknown is in the flask. And to that flask, we add an indicator. And what an indicator does is when it reaches a certain point, a point of equilibrium, it then turns a color. And you have to be very careful when you're looking for this color change because it happens very quick. When we reach that color, we're dropping in a solution. That solution we know the concentration of. When we reach equilibrium, we can then calculate the concentration of the unknown. So in this case, the flask contained an acid of unknown concentration. We then added an indicator to the acid. In this case, based on the color, it's phenolphthalein, which turns like a a pinkish color. In the burette. Now, a burette is like a giant pipette. It's got a little stopcock on it. And what you do is you kind of turn that to allow a drop, drop, drop. And with every drop you're adding a small amount of a known concentration. In this case, it is sodium hydroxide, a base, to react with that acid. Now, we know from our acid-base reactions that this produces water and a salt. It also looks at the indicator point. And when we reach that point of equilibrium, we have a color change. Okay. And our last slide. So if we look at the flow chart, the volume of a standard solution that's in the burette, the tall part, we can then use that to calculate the concentration of an unknown solution by going through our reaction. If it's an acid and a base, we can figure out the concentrations through molar relationships. Solution of known concentration is called the standard solution. It's used to determine the unknown concentration of another solution. The reaction will reach and change color at the equivalence point where equilibrium is reached. All right, everybody. keep up with your reading. Check those answers. They're in teams for the book. Don't worry. We can always go over stuff when you come back. I'll be more than happy to answer any questions. Guys, have a wonderful remainder of your break. Enjoy yourselves. You guys are doing great so far. Keep up the good work. And that is about it. Everybody be safe out there. I will see you guys all in class. All right. Bye, everybody.